Well, good morning, good afternoon, or good evening, wherever you are today. In this lesson, we're going to talk about the Gaussian Elimination method, also known as GEM. So let's get into it. GEM, the Gauss Elimination method, is the process of transforming an augmented matrix to a simpler, what we'll call a U-form augmented matrix with the same solutions as the original. And so this is how a U-form augmented matrix will work. Understanding, of course, that the number of columns might not match the number of rows. But what we try to do is we try to get as much of the diagonal as possible as ones, and anything below that diagonal to be a zero. That's called an upper matrix. And so that's going to be important in the future, because in the future we're going to encounter what are called lower matrices, L matrices, and U matrices, which are these upper matrices. We won't have to worry about that for quite some time, but that's what we're going to be covering much later. Okay, so again, U in this case is also known as an upper matrix. Now, there are the two properties of the U matrix that we desire. First are the zeros are below the diagonal, and the diagonal is made up of ones. That's what's most desirable. The key here is that the solutions of the new augmented matrix are the same as the original augmented matrix. So we are looking for the solutions to the original, but if we can transform that system or that augmented matrix into a simpler model, then the solutions can be more easily obtained. So one of the things I want you to realize is that there's a little bit of work that goes into this, specifically when we do it by hand. And so in this example, we're going to use GEM on the given augmented matrix, and then we're going to use something called backward substitution to solve the linear system. So step one, let's go ahead and transform the system, the linear system that we have here, into an augmented matrix. So the way that this works is 1, 2, 0, 1, 1, 1, 3, negative 1, 2, and then the coefficient column is 12, 2, 7. Now, what we're going to do is we're going to label the rows. And so here's row 1, row 2, and row 3. I'm going to use R1, R2, and R3 to label the different rows, because now I'm going to write out the kind of calculations that I want to do using these labels here. The first thing I want to do is I want to get a 0 in this position here where there's the 2. So here's how I'm going to do that. I'm going to take negative 2 times row 1. I'm going to add this to row 2. And this is going to give me a brand new row 2. And so the star that I've just written here, the asterisk that I've just written here, represents new. New. So this is new row 2. Now, you can take any linear combination of rows to create a new row. You can multiply any row that you want by a non-zero constant. That's a rule that you can do. So, before I proceed with that calculation, let's go ahead and at least write out some of the rules here. You may multiply any row by a non-zero constant. You may swap any two rows. You may perform a linear combination on any number of rows to produce a new row. But this rule here does come with an exception. And here's the exception. So for example, I'm using a linear combination of negative 2 times row 1 plus row 2. And what that means is this. I may use that linear combination to replace either row 1 or row 2, but not row 3. So if you don't use a row in the linear combination, you can't replace that row after the linear combination's done. And so that's the exception. So if I perform negative 2 times row 1, which means all of these numbers here are multiplied by negative 2, and then they're added to row 2, that's going to give me a brand new row 2. So let's see what that looks like. Now, remember, I'm replacing row 2, not row 1. So even though I've used this linear combination of -2 times row 1, I don't have to write -2 times row 1 because I'm not replacing it. So I can just write the numbers down like so. But now I am replacing row 2. So this becomes a 0. This becomes a -1. This becomes a -7. And this becomes a -22. And now I've got zeros underneath the very first column, the very first one in the first column. Now the objective is to try and get a 1 here in this position right here. So what I'm going to do now is I'm going to swap. So I'm going to swap row 2 or interchange rows 2 and row 3. So now this becomes 1, 1, 3, 12, 0, 1, 2, 7, 0, -1, -7, -22. And the solutions to this system have not changed. Now I desire to get a 0 here. So to get a 0 here, I'm going to take row 2 plus row 3, and that's going to give me a brand new row 3. So now I can write the old row 1 and the old row 2 because I'm not replacing them. But I am replacing row 3, so this becomes 0, 0, -5, and then -15. Now I desire to get a 1 in this position right here. So all I have to do is take -1/5 of row 3, and that's going to give me a brand new row 3. And so now I rewrite rows 1 and 2 just as they were before. Row 3 now becomes 1 and 3. And now is the time to remember what this augmented system meant. So let's translate this back into a linear system. It already is a linear system, but let's write this into the traditional linear system that we know and love. So this is x1 plus x2 plus 3x3 equals 12. And then x2 plus 2x3 equals 7. And here's where it gets really interesting. The last row is x3 equals 3. So we just solved for x3. We know the value of x3. And so now what we're going to do is we're going to perform something called backward substitution. So now that we have x3 equals 3, let's substitute that into the middle equation. x2 plus 2 times 3 equals 7, and that means that x2 equals 1. Now we know the value of x2 and x3, so we backward substitute that into the first equation. x1 plus 1 plus 3 times 3 equals 12, and this means that x1 equals 2. And now we have the solution to the system. It's the ordered triple 2, 1, 3. Okay, that is the GEM, the Gaussian Elimination method. So let's go back and review real quick what the objective was here. We're transforming the original system, which is this right here. That's the original system. And we're transforming it into a U matrix, an upper matrix, where the lower part of that matrix is zeros and the diagonals are 1, like this. The diagonal is 1. And then we perform something called backwards substitution. We go backwards, substituting in the values that we know to obtain the values that we don't know. And so that is the essence of GEM, Gaussian Elimination method. Okay, it's probably now good to do a video on how to use the Gaussian Elimination method computationally on a computer. So the language we're going to use for that lesson is going to be Python. God bless you wherever you are today.